Hello. Last classes we have seen about the logic gates, Boolean function minimization using Boolean identities. The logic gates that we have seen, the common logic gates are AND, OR and NOT gates, and these are the symbols for the AND, OR and NOT gates. And we have also seen the truth tables related to these logic operations, X and Y, X or Y, not X. X and Y will give the output as true. When all the inputs are true, the output will be true. X or Y is nothing but it is true when any one of the inputs is true, and not is the inversion of the input. That is, if the input is 0, output will be 1. If input is 1, output will be 0. And coming to the logic gate XOR, that is exclusive OR or XOR. It is not the reverse of OR gate. It says that it is true only when the inputs differ. That is, if you see here the truth table, if X, Y are both same, that is if both are zeros or both are ones, the output is 0. If they differ, that is if X is equal to 0 and Y equal to 1, or when X is 1 and Y is 0, the output is true, that is X exclusive or Y is 1. And the symbol for the logic gate is this. It is taking the inputs X, Y, and the output of this XOR gate is X XOR Y. The symbol for the XOR is plus circled plus. And the logic gates can take 2 or more than 2 inputs. That is, here you can see the OR gate taking more than 2 inputs, AND gate taking more than 2 inputs, that is 3 inputs, and can also result 1 or more than 1 outputs. The third figure says that it is resulting in more than 1 output. And coming to the logic diagram, that is, in logic diagram we use the logic gates in order to represent the Boolean expression or the Boolean function. Here the Boolean function is given as X or Y complement Z. Y complement, the input is Y complement, so we use an inverter here, that is NOT gate for the input Y, and Y complement Z, that is between Y complement Z we use a AND gate. So that is why you can see a inverter, and that inverted output Y complement and Z is given as inputs to the AND gate that gives the output Y complement Z. That is given as the input to the OR gate along with X or Y complement Z. And the final output of this will be the expression X or Y complement Z. This is how, using the logic gates, we draw the logic diagrams. Then coming to the minimization, the other method we have seen previously, Boolean expression minimization using Boolean identities. Now we have another method, that is coordinate map. Using coordinate map, minimizing the Boolean expressions. When we are minimizing using the map will have cells. It is collection of cells. And how many number of cells we need to take in the coordinate map? If there is an expression, 3 variable expression, let us suppose the previous expression f of x comma y comma z. Here in this expression we are using 3 variables. When there are 3 variables, we use 2 power 3 number of cells, that is 8 cells in the coordinate map. If there are only 2 variables, that is if there is an expression f of x comma y equal to x plus y, then we take a 2 variable map, where a 2 variable map will have 2 power 2 number of cells, that is 4 cells in the map. If there are 4 variables in the expression, the number of cells will be 2 power 4, that is 16 cells in the coordinate map. That is, n variable expression will have 2 power n number of cells in the coordinate map. A 3 variable k map is given here. A, B, C are the variables in the expression. A can have the values 0 or 1. B, C can have 0, 0, 0, 1, 1, 1, 1, 0. So this is how we represent a coordinate map for 3 variable expression. In the next coming classes, we will see how to draw the coordinate map and how to minimize Boolean functions using coordinate map. Thank you.